Don't forget though, if, let's say I had, with some difficulty, I prepare a chamber of hydrogen atoms, they'd be in their ground state, but I shine a bunch of light on them to put them in the 2p state. And let's say I just used a ton of energy, so they're all in the 2p state. I could do spectroscopy on the 2p hydrogens, and I could see them transition to 3s. I could do that kind of chicanery as well. Anything else that I can't, it seems like I was going to review a little bit, but it looks like I haven't. Any other questions about, was that all you were thinking of? Yeah, that's a funny one, because it doesn't come out of the quantum mechanical calculation, it's just a practical one. Okay, so again, let me also do a little bit of reviewing here, what we were talking about last time. I just got into introducing multi-electron stuff, which includes everything that's not hydrogen, which is basically everything. Remember, hydrogen is not just H. If I have my little magical chamber of H that I was just talking about, actually it'll just dimerize and form H2. So H doesn't really exist, but it certainly is, it's the best starting point we have. So the context I do this lecture and on your homework is I talk about an H- atom, so it has 2 electrons. That would work for helium as well. I just call it H- just for the hell of it, really. There's no reason for that. And everything I'm showing you applies to more complex things in molecules. The core principles that we're covering today apply to everything, but they literally just get more complex. I'm going to show you how the complexity scales up, the complexity of dealing with multiple electrons. It actually really gets bad. But hopefully this will be kind of interesting, because this is one of the more fascinating things about quantum mechanics as it applies to, real things. So Hamiltonian, now last time you all were comfortable with the fact that that is the kinetic energy. I don't think I ever mentioned specifically del. It's a well-known mathematical symbol for a derivative, basically. So I squared it. Don't forget that we're still in radial, so this is our 1 over r, ddr, 1 r, all that jazz. The sines and 1 over sine, dd theta, sine, dd theta, all of that's in here. Now, another thing I want to point out is that when you've got, I've got 1s and 2s for electron 1 and electron 2. The way that works is, if we're doing like an average value, if we're calculating the energy of, say, of an H- anion, multi-electron, what you end up with, it would be just a valuation with electron 1, and then you'd have another evaluation with electron 2. So sorry, I'm not writing this out, but so you basically end up with 2 integrals for everything. You used to have a single integral, you now have 2 integrals. It just partitions up based on R1 and R2. So it's really no different than like when you integrated dr, and you had stuff and you integrated dr, and you had other stuff and you did this, and then you did this. Now you've got twice as many because you have 2 electrons. So and you'll see that on the homework if that's a little bit confusing and cloudy. It'll get fixed. Okay, so anyway, all of this is fine. The wave function would just simply be 1 for the first electron, 1 for the second electron. All of that would be sensible. It would be relatively easy to solve. Then this comes along, the Coulombic interaction between the 2 electrons. It's a very strong interaction. It's very powerful. I mean, to be blunt, we'd like to ignore it. There's actually a couple other things I could add here, and I'll show you some of those. There's a couple of weird things like interaction of the magnet. So there's another term here that I could add to the Hamiltonian, which is the electron's interaction with the magnetism of the nucleus. So I'm not going to put that on there. It's a really small thing. If you have to do real fine spectroscopy, you can see that there's this interaction with the magnetic parts of the electron and proton and stuff like that. They're really small. They don't really affect much. So I just leave them out. This, no, we cannot remove that. And because we tend to do this abbreviation, we call it R12. It's not separable. I mean, there's no approximation you can make. I can't just say, oh, well, this is close enough to something that is separable. It's not separable. We're completely screwed. And that's, seriously, that's the answer. No one has ever figured out around the problem of the inseparability of the Coulomb operator between two electrons, let alone 3 or 4 and blah, blah, blah. That means you cannot do this. And that means we also have no way of solving the wave functions. No way whatsoever. So the answer is to do it anyway. Seriously, this is the best humanity has ever come up with. Just do it anyway. It's wrong on so many levels. The error of doing so, now let me tell you a little bit about what happens as a result of intentionally making a mistake. The reason that you have a problem is, and this will hopefully make it a little bit more clear what separability is. These two electrons can't overlap each other, right? That's nuclear explosion that destroys the universe. Okay? 1/0 is a big number, and this is energy. So if these two literally slam right into each other and overlap each other, the amount of energy released is the biggest explosion, greater than the Big Bang, right? Even the Big Bang had finite energy, a lot, but that would be infinite energy. They cannot touch each other. Okay, so if I write the wave function as like a 2s state, so this is e to the minus r over a Bohr, and this is e to the minus r1 over a Bohr, and that's e to the minus r2 over a Bohr, and they're on the same atom. The thing is that there has to be like a more complex expression such that r1 never touches r2. They can't be the same number. They can't overlap each other. Now how do you do that? Right? Because this thing is whizzing around this proton, and so the other guy is too, but you have to have some kind of mathematical function that never lets them touch each other, but that's really complicated because they're everywhere at once. And the answer, if you're thinking like, well, okay, maybe we could just, no, forget it. No one has ever figured this out, right? No one can, it's not possible. Okay, so that's where you get a major problem, is that the electrons can overlap. Don't know why my hand spelling is bad. Too much on my mind. Anyway, the electrons can overlap. And that's mega bad for all the reasons I said. Now, it won't result in a catastrophic end of the universe. What it does result, it's surprisingly not so bad. You get about a 1% error. You get a 1% error in the energy from doing that, from allowing the electrons to get too close to each other. Actually, I guess maybe the universe doesn't explode because for them to be completely overlapped requires 2 points in space to have the same volume, but points in space don't have volume. Euclidean geometry, anyway. So it's not quite end of the world bad, but it's 1% bad. So it sounds like this error isn't too terrible, but that is equivalent to a chemical bond. I don't know what's wrong with me today. I'm writing terribly. It's equivalent to a chemical bond. So remember that this Hamiltonian describes the electron's interaction with the proton, its own ability to whiz around, if it is whizzing around. There's a lot that goes on inside of an atom. Chemical bonds are they're relatively small, and by small I mean about 1% perturbation to the atom. Bondings don't really matter so much to the overall atom. It's a small part of the atom's energetic life. It turns out that it's on par with the error of doing this by solving electronic structure this way. Uh-oh. Okay, now you partition scientists into two camps. Physicists who say, well, look, we're trying to understand the entire atom, so a 1% error is not bad. Chemists who only care about this. Well, guess what? So this for us is a major, major problem. Now, what I don't want to confuse you about, though, is that this doesn't mean that it doesn't predict bonding. If we start putting in water, let's put in water, so we have to add a bunch more electrons, but whatever, I think you could just add more terms, right? So let's make this thing for water. Let's ask, what does it look like? Does it have bonds or not? It does, but where you really get a bit of a problem is if you want to apply this, what would you apply it for? You would apply it for thermochemistry, for chemical reactions, right? And that, again, chemists, right? So what I want to do is calculate the energy of water minus that of H2 and O2, and now I know the internal energy of forming water. Right now I can fill out thermodynamic data tables without ever actually having to do the reaction. Now I've already done a bunch of reactions, already collected a bunch of data, but I can honestly tell you there's a whole bunch of other things I would like to try in my lab that I cannot find in the data table, and if I could just query it on a computer, I would find that infinitely useful. But the numbers are not good. So that's a real pain in the rear end, and this is, by the way, maybe I'll say a little bit about how people are trying to fix this, but if you go into grad school and you become a theoretician, guess what you're working on? That almost all theoreticians in physical chemistry work on solutions to this problem. And they've had good progress. There's no perfect solution, there's fixes. And the fixes have varying degrees of finesse that get this down to like 0.001%, some 0.0001%. That is good enough for predicting chemical bonds. Now, can you imagine what the problem with that is? Supercomputer. It requires a supercomputer. Not everyone has a supercomputer. So anyway, well, that's all I wanted to say about that. And again, this is, I know you're like, oh, whatever, but to someone who does this as a living, this is like the biggest problem we have. All right, the next thing I wanted to talk about was, okay, now you know what this is. So here's a hydrogen 1s, and you got a 2s. I'm not writing this very well. I'm just saying, for example, now don't forget things like, I'm sure this will be on the test. Remember that the P's are degenerate with the S, and here's the 3S, here's the 3P, and then we have 3Ds and all that. So I'm writing a configuration, and then I want to start writing the wave function for that. And this is where, now this is the part I hope you find this kind of interesting, because there's a little bit of a problem when it comes to all of this. So electrons are spin 1/2. Remember, spin is a type of angular momentum that we don't understand what it really is. It just behaves like angular momentum. And it's this intrinsic thing that electrons have. Protons and neutrons are also spin 1/2. Photons are spin 1. The Higgs boson, actually that's spin 0. Remember I was saying that spin 1/2 things are responsible, quarks are spin 1/2. There are all these things that are spin 1/2, and those are fermions, and those build matter into this universe. The spin 1 things are responsible for force. Those include photons. Photons, that's transmitting energy. That's energy is force. And things like Higgs boson, which are responsible for gravity. And anyway, now it turns out that another thing we figured out, I don't know that it plops out of the theory like a quantum number, but these cannot be in same state. So they cannot be in the same state. Again, I don't know what's wrong with my handwriting today. I can't help it. You gotta see a medical doctor, but they cannot be in the same state. So what? Now, if I'm looking at this guy right here, if I'm looking at let's say this is either a helium or an H- atom, say it's H-. It looks to me like the electrons are in the same state. They're both in a 1s. But the solution, of course, is what? I've drawn it.
They're different spin ups and spin downs.
Right. Spin up and spin down, that counts. I know it sounds like cheating, but it counts. So it's right. We know that's right. So, I mean, a lot of things we don't know, but we know spin is real and spin up, spin down. Remember that, like the L quantum number has M sub L. L of 1 has M -1, 0, and +1, Px, Py, Pz. Spin 1/2 implies that there's a sub levels, right? And that can only be up and down. Spin -1/2, spin +1/2. A sub-spin, a sub-angular number, and so that's where you get those. And those are the mechanism by which we keep things from being in the same state at the same time. But now the way that works is and this is going to sound kind of silly. So now I'm also trying to get you used to, when I say a wave function, I'm now having to decompose it into a wave functions for one particle and another. So now let me add spin and see what that does. Okay, so the way I would do that, I would just want to say that the 1s, that one of the 1s, well, I'll be very specific. I'll actually call that a 1s. That 1s orbital has an alpha spin, and that the other electron is also in a 1s orbital. Now it's the other electron, so I call that 2, and it's spin down. Okay, so bammo. Now I have magically kept these things from being in the same state. Now this thing, as usual, is a normalization constant, e to the minus r1 over a naught. I kind of have the S state memorized, r1 over a naught. There's no angle. The angle stuff is just a constant, so there's nothing to write there. Then the spin, remember, is just, I went over this last time, so I'm kind of reviewing. We don't know what spin is. We have no idea what spin is, so its wave function is a symbol, just like Prince's name before he died. It's just a symbol. Sorry, that looks awful. Oh, it's with me today. Yeah, it's a little bit better. Remember, A naught is a Bohr. And then, of course, the other guy is the same. Now, when you write all this out, don't forget you're going to need to renormalize it. Not a big deal. You should know how to do that. But you also know that that normalizations sometimes don't really matter, especially if we're doing like eigenvalue calculations. You can actually just call it a big M and forget about it. Okay, so that seems to have solved the problem, but no, it actually hasn't. So when people first figured out quantum mechanics, some of the people after like Schrodinger and Heisenberg, these were some of the big names, this Dirac person, when they figured out the core part of kinetic energy and eigenvalue equations and what are wave functions for, you had another generation kind of kick in around the 40s. And they started like, well, okay, well, I mean, if any of this is worth anything, I'll start trying to figure out about bonds and stuff. And they wrote the wave functions this way because that's purely sensible. And they got some results okay, but actually a lot. When they got to helium, all of a sudden the results were not good. So like they would get the right energy for hydrogen, but they didn't for helium. Something was way off, and they were lost for the longest time. It turns out that fermions, for two particles, two fermions, I'm talking about electrons, to not be in the same state at the same time requires this property. And I'll explain why that this property, this is going to sound like nutso. Like, why in God's name are you writing this? And I'll explain why in a second. Let me just write it down. So again, I'm going to stick with two particles, right? Forget spin, that's not important. Let's just assume that spin is in there, not important. Okay, there's a wave function for one, there's a second wave function for the other one. They both could be 1s, maybe that's 1s, and maybe that's 2s or 2p, yeah, whatever. Okay, the way to handle this fermion deal is to require this to happen. If you change, now get this is going to sound nuts, but I am saying this correctly, it's just hard to interpret. If I take all the labels for electron 1, R1, theta 1, C1, I'm not writing the thetas and phis because if I change all those ones, literally write out the wave function, and I have a bunch of R1s and theta 1s and R2s and thetas 2s, I erase them. Wherever I see a 1, I put a 2. And wherever I see an R2, I put a 1. I write out the wave function. Here, I'll do it on this. Wherever I see an R1 or anything that designates the first electron, I write a 2. And wherever I see a 2, I erase it and I put a 1. Okay, if I do that, I have got to have a minus sign pop out. It's got to be equal to the same thing with a minus sign. Does that make sense?
No.
I know, it makes no sense whatsoever, does it? Like, what the hell does this atom care about my R1s or R2s? About my ability to use an eraser to erase a 2 and write a 1 and a 1 and a 2? Why could that possibly matter? Okay, this is nutso, and I'm going to have you repeat what I'm about to show you on the homework just so you really get it. It turns out for this reason. Okay, you're going to kind of like this. I hope you kind of like this. Okay. Now, let's say, and why does this work? Okay, I'm going to take this thing, and let's say psi 2 is equal to psi 1. In other words, I'm going to put them in the same state. So this would be like, okay, so here's 1s, here's 2s, da 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 da. If they're going to be in the same state, so they both have to be in a 1s orbital, okay. But if they're in the same state, they'd have to be both spin up. Okay, so these are in the same state. Now remember, for reasons that we don't really know, no. The great turkey in the sky that threw an electron at a barrier and all that jazz has dictated to us turkey creatures that this is not allowed. How does this permutation, this is called antisymmetry to permutation, this is called antisymmetry to permutation. How does that enforce that? Well, watch this. All right, so what I'm going to do is I'm going to turn all the psi 2's into psi 1. Sorry, that's still a 2, right? Okay, so again, what I call the wave function is just the isn't a s orbital or a p orbital and whatnot. Okay, there's a minus sign. Okay. All right. So again, I said that these things, by designating this to be the same as that, I'm just calling them both 1s orbitals. Not hard, right? I'm saying they're both spin up. Now you've learned in high school that that's not allowed, and that's what I'm trying to prove. Why is that? Well, now look closely at this. Let's call this the letter A. Psi 1 R1, psi 1 R2. Okay, look at this. Psi 1 R1, psi 1 R2. Right, but yeah, but it's the same thing. Now remember, A times B is equal to B times A. Middle school, right? You know that. So I have A equal to minus A. Now, when is that true? What is A? If I ever wrote this equation for you, let's not worry about imaginary numbers or 3 dimensions. Tell me what A is that makes this true.
0.
Right, there you go. Okay, so here's a big lesson. I can't write this down because my handwriting is awful. This thing, okay, this is a big deal. This is the antisymmetry to exchange principle. As much as that sounds like ridiculous and arbitrary, what it does is it forces, if you make sure that you follow this principle and you screw up and write an electronic configuration that's not allowed, but follow the proper rules, you will find that you wrote a wave function that is actually equal to 0. And I have you do it on the homework so that you will see that. I'm not going to give you an example because you're going to do it on the homework. But again, I want to point that out, that if you screw up, but write it out correctly despite having screwed up, it catches you because you actually wrote down 0. And again, on the homework, you're going to do that. And you're going to do that by actually kind of exactly what I just, anyway, you'll see. I'm going to post it again kind of like. All right, so now what does that look like? Now this is all, right now, you probably should be still a little bit confused because I've not gone into enough detail to make this like sensible, so now I'm going to do that. Now to do that, what I'm going to do is I'm going to get a little bit more specific and start writing out wave functions that have this property because this doesn't do that. Like how does, right? Okay, so now here's the challenge is to figure out how do you write wave functions that will behave with this antisymmetry deal. And I'm just going to get rid of all of this. And this isn't hard for 2 electrons. And then on the homework, I'll have you do 30 electrons. It's not hard. You're going to kind of laugh when you see how easy it is. And then you're going to cry on the homework when I have you do it for 3 electrons, and then you're see how easy it not is. Okay, let's see, what do I want to do first? I'm going to do, I write these configurations, by the way, because the last few classes, and don't forget that these are P's, the last few classes I've had choked violently on the tests. They seem to just not have understood. I'm still burned on this. So many students said that hydrogen only exists in the 1s state and the others are wrong. Huh? No. Anyway, so what do I want to do? I want to do this one. Ground state of H minus. Ground state, of course, both electrons are in the lowest orbital, but they can't be in the same state at the same time, so they're in different spin states. So I've done this correctly for whatever reason H minus exists. Okay, now I've got 2 ways to make antisymmetrics. 2 ways to make antisymmetric. Now remember, that's antisymmetric to interchange, but my handwriting is so bad, my speaking is bad today too, but I'm not gonna write that out. So anyway, 2 ways to make antisymmetric to interchange. It turns out that, let's see, for this, I'm gonna call this, you've seen this before, I'm gonna call this a 1s2 configuration. You should have had that in high school when you looked at atomic configuration and you learned this notation. First shell, S state, 2 electrons, right? It's kind of obvious. Even if you didn't see that before, it's kind of obvious. Okay, now there's 2 ways for spin up and spin down, which I call a singlet. You've heard that term, singlet, triplet, right? You're familiar with phosphorescence being from triplet states and fluorescence from singlet. Yeah, you have heard that before, right? I'm going to go over it again, but I see a little, okay. I'm going to go over it again, but so anyway. So in this configuration, this is called a singlet. Oh, by the way, the singlet state, now why is that? Because if you add up all the S's, you got 1/2 H bar plus minus 1/2 H bar, and that's 0. So the net sum of the spins, spin up, spin down, is 0. So I call that a singlet. So that's why. If kind of should have seen that before. I don't know what all your previous instructors have shown you or not. Okay, when it comes to a singlet state, the way to do this is to work with the spins. Work with spins. Okay, now what that means is I'm just going to write this out so that I'm kind of babbling like an idiot. So, okay. Recall that, now before I know I was saying I was absorbing all of these space and spin wave functions in the symbol, and now I'm going to separate them again. Okay, so now I'm going to write out the spin wave functions. And here's how I do that. Now, one is spin up, the other is spin down, and then I permute them. Okay, which is funky. The funky way to write this. Yeah, I did it right. It's a funky way to write this. It's like, where is, this guy is cool, I get this. The first electron's in its first orbital. That's fine. It's spin up. But then there's this component that says it's simultaneously spin down. And that's where quantum, this is the part of quantum mechanics where I told you this. There are some things I can't explain away with, like, oh, it's like when the car speeds up in the wintertime. Remember last semester? I got nothing to explain why the heck this should make sense, other than once they started writing out wave functions this way back in the 40s, like for helium and whatnot. I mentioned before that before they did this, they got answers that weren't quite right. When they did this, their answers were dead on, in terms of like energies and whatnot, spectroscopy. As soon as they did this, everything started working again. They knew it was right. And I'll show you how to extend it to 3 electrons. Okay, now note, what happens if I do this? Do I get minus that? So now remember, I'm only permuting the labels on on the coordinates. Okay, so, and this guy doesn't matter, they're both 1s. These are indistinguishable. Let's say that they're both 1s states. Okay, now I've got alpha 2, beta 1, minus alpha 1, beta 2. Okay, my question to you is this minus that? Don't worry about the spins, they don't do anything, huh? What do you think, huh? Is this minus that?
Are you saying that they're opposites?
No, hold on. Now remember, what I've done is I've taken this and I've permuted the labels. Again, arbitrary. What the hell with this permuting the labels? Why would that have an effect? Again, because it prevents two electrons from actually being in the same state at the same time. Now this guy should be cool. I've written it out right. I'm just asking, is it? Having permuted the labels here, is it minus that? That's the question. Is this minus that?
It's hidden in the this. That is the negative of the thing above it. Yeah.
Is it? Minus alpha 2 beta 1 plus alpha 2 beta 1 minus alpha 1 beta 2 plus alpha 1 beta 2. Right. This is minus, this is minus that. So I was doing that in Chinese, but anyway, that's minus that. There you go. It works. I took the wave function, I wrote it out properly. I then permuted it to see whether I'd pick up a minus sign on the same thing, and in fact, I do. So why do I write this? As much as this is like, what the hell does that mean? I don't know. That's quantum for you. But I do know I picked up a minus sign when I switched all the 1s and 2s. There you go. Now let me point that, now you got that? You got that? Right? That good question?
Why does it not matter that your wavelengths?
Well, now hold on. Now this
Wave function, sorry.
The wave function. I know what you mean. All right, let's say they're both 1s.
Okay.
Right, they don't matter. This is e to the I. This is e to the minus r1. This is e to the minus r2. And that's e to the minus r1. This is e to the minus r1. That's e to the minus r2.
Got it.
AB is equal to BA.
So all you're showing with this is that the wave function 1, 2 is equal to the negative wave function 2, 1?
Yes,
okay.
Right. Now, again, the thing is, you've got to remember that there's nothing physical. And again, this is the thing that slays me. It's why I don't like teaching this class. God, I hate this. I always told you that when I mess around with equations, it means something. This time it doesn't. This is the only time I can say that, not to my knowledge. That I just simply erased. I erased 1s and I put a 2 and I erased a 2 and I put a 1. What does that physically mean? I don't think it means anything. But it has the effect of making sure I don't write the wave function in a way that can't happen. I'll give you an example. Okay, so now this guy, this is good. Let's be very primitive. This is good. Now let me write bad. Let me write a bad one. Okay. Now again, what I'm going to have to do, I'm going to have to describe a configuration that I should not be describing. Now this part, there's nothing going on with this part. But now let me ask you this. How do I turn this? Let's keep it simple. Let's keep these both in the 1s state. There's 2 electrons that can be in the 1s state. How do I make this such that no? What do I do? Make them both spin up, right? Right? Not good, right? You can't do that. All right, now let me write the proper antisymmetric wave function. Remember the beta became an alpha. Huh? What's that? 0. Right, 0. No. You see? Clever, huh? It actually works. By writing this wave function out such that this passes, it guarantees if you mess up, you should know because you'll end up with 0. That is the whole philosophy behind all this, right? It still slays me that this process makes it doesn't make any sense, but it does do something that ultimately makes sense, which is my description of a configuration that I can't do will render 0, preventing me from making that happen, basically. So So anyway, that's my long-winded explanation of multi-electron wave functions. And then you can operate on them, and I'll have you do some spin operations and whatnot. I'll have you do that on the homework because I think that's actually going to be a little bit more instructive. It's basically, again, I kind of, the homework is really long worded, but it's actually, I don't think, any harder than any other. It's just that I'm very repetitive about what I'm saying right now, and I'm doing that to really build into your head, and I just kind of want to see if that works or not. Okay, now let me tell you how, there's a few things here that I should have done. This isn't a big deal, and I've said this many times, but technically I need to divide by the square root of 2 because I've doubled the size of the wave function. Don't worry about that. I just, on the homework I put the square root of 2. It's really supposed to be there. But again, normalization wipes that out anyway. It's, I need to put it, I really should put it there. You find it that way on textbooks. Question.
Does that just works for the S or also for the E and Z?
Yes, for 2 electrons if the spins are paired. So when they're unpaired, you have a different thing happening. So I'll explain that in 1 second. Let me just show you real quick that there's a shorthand way of doing this. I'm still talking about a singlet state where spins are paired, and then we'll do 2 electrons unpaired, and that actually is completely different. So, nutty. Actually, when you're doing calculations, like when you buy this software, there's a software called Gaussian, there's another one called QChem. Academics write this software. Whenever you're describing a molecule, you have to tell it whether you're singlet or not singlet, because it does everything differently based on that. So, in terms of like making sure you don't screw this up, there's a handy-dandy way to do this, just called a Slater determinant. John Slater was my advisor's advisor, by the way, so I thought that was kind of neat. Okay, a wave function, you write it as the determinant. Again, I don't like to mess little details up if I can help it. Is the determinant of a matrix. The way to construct a matrix, and you might want to pay attention to this because this is half your homework, is, let's see, let me just start out, let me do a 1s state. So I'm writing in the 1-1 element. Okay, and again, I'm just going to do 2 electrons, and I'll show you how to do 3 electrons, which is on your homework. And I bet you forgot what the determinant of a matrix is. I'll show you that. I bet you forgot. It's okay. Okay. I know I've got orbital, and then I've got spin, and I've got 2 electrons. It turns out that if you go this way, it's electrons. So that means that this next one is for R2. And 2, there we go. Okay. So notice that I didn't switch any of the wave function parts. I switched the labels on the electrons. Now that would then mean down are for the size. Now that would mean that while I've made, I'll tell you what, you know what, let me not be specific about what wave state is what. That can get confusing. Let me just call it 1. It could be a 1s, it could be a 2s. Okay, now this next guy, now I've done wave function 1, spin 1. Now, because electrons go this way, I just made all the 1s, 2s for the electrons, but I kept the wave functions and the spin wave functions the same. Now I'm going to change that, but this is still the column for R1 for the first electron. So I'm changing the wave function bits, but I'm not changing the electron labels. So I know that gets a little bit, that'll make your head spin a little bit, but just stare at this long enough and it's kind of sensible, right? So again, the R1s and alpha 1s still turn into R2s and alpha 2s, but the alphas and wave functions are the same. The electrons stay in the same column. What changes are the wave functions. Now the determinant is then this times that minus that times that. All right, remember that? Let me just write that down. A, B, C, D is A, B minus C, B. Okay, so then that ends up, if you do that, it's same as above. Okay, let me just, I'll verify that. I did not use time very well today. I really screwed up time. I'm going to show you how to do spin wave function. Triplets are kind of neat. So it turns out that oh, wait. Yeah, there's another, damn it, there's another part to this I have to show you. Oh, damn it, I forgot about this. Yeah, let me just write it out. Alpha 1, beta 2, minus psi 1, R, psi 2, R1, alpha 2, beta 1. Okay. Yeah, minus that. Okay. All right. I hate to admit this, but it turns out that there is another layer complication. Normally, I don't cover this because I want to simplify this, but it turns out that the space wave functions have to have a property, another property, which is indistinct. It's called indistinguishability to interchange. God, I keep forgetting this. I know, I swear to God, you know I try not to gloss things over. I try to gloss this one over because I freaking hate it. It turns out that the way I wrote it at first up here, the problem is that you can distinguish between electron 1 and electron 2. No, they're electrons. It's like I can distinguish my two cats, but because they're cats, they have different color fur. But electrons, you could not do that. So you actually have to write them out this way. Notice that it's symmetric, but the R1s and R2s are switched. And again, that just means that the electrons are not separate. This, by the way, does next to nothing. However, the alphas are factored out correctly. Beta 2 minus alpha 2, beta 1. Damn, I forget that every single time. I hate that it does that. It's just annoying. And I just screwed it again. I screwed that up and forgot it. Okay, all right.